The way to get started is to quit talking and begin doing. A very fine evening to all the viewers. It is my great pleasure in welcoming you all for this online webinar session organized by the Department of Mechanical Engineering. First and foremost, I would like to thank the Almighty for making this event possible. Myself, Ram Kumar, Assistant Professor in the department. I feel honored and privileged to get this opportunity in sharing a few words about our college and our department with all of you. Francis Xavier Engineering College is popularly known as FX Engineering College, which is located at heart of Tirunelveli city, and it was established in the year 2000. FX Engineering College comes under the SCAD group of institutions. Our institution has been offered autonomous status in the year 2019. We offer 6 UG programs, 10 PG programs and research centers. Our college has achieved many awards. Among all, I would like to list a few to your knowledge. We got gold category for Industry Linked Technical Institute, which was awarded by AICTE CII survey. In Chronicle Engineering College survey, we achieved 3rd position among 19 engineering colleges in India. In Times Best Engineering College, our college has obtained 15th rank in Tamil Nadu and 108th rank in India. Apart from all, we got ICT Academy, Tamil Nadu Academic Partner Excellence Award in 2017. Regarding the Department of Mechanical Engineering, it is the largest department on campus with 600 plus students, 35 faculty members and with good infrastructure facilities. We offer BE in Mechanical Engineering, ME in Industrial Safety Engineering. The UG program was accredited by NBA, the National Board of Accreditation. We have Fanuc Center of Excellence for CNC Center, BMW and Hyundai supported mechanical labs. Our department has signed many MOUs with the leading manufacturing and service industries. Apart from regular activities, our student has been trained and imparted with various skill training programs and value-added courses. The special feature of our department is the establishment of 3 applied laboratories in addition to the regular labs. The purpose of this lab is to inculcate the students with innovative skills which is required by the industry. We offer international certified program in CAD and NDT. We have also organized many international conferences, workshops and funded seminars. Today, we are organizing this webinar on adventure of particle physics. I hope this session will be more useful for all of us. Thank you.
that many of you are studying and are doing engineering studies, or are at least interested in the field of science and engineering. So I am assuming that being a particle physicist is something that you are definitely wondering, why do I call it an adventure? So the adventure is indeed starting from the very, very beginning, when one thinks about how to move in your career, which are the scientific fields that interest me, and which are the fields that really excite me. And that's the thrill that I have had over the last 30 years, as was kindly described by our chair, that this is the excitement that I would like to share with you. So you can see here many names which you recognize. And what is common in these names? Like Professor Raman, Satyendrath Bose, Dr. Bhabha, Subramaniam Chandrasekharji, Meghnad Saha, Ramanujam, Vikram Sarabhai, Professor Kalam, Dr. Narlikar, and so many others, G.N. Ramachandran. So what is common here? The common part is really to be very curious, and they have questions. They have been looking for knowledge and trying to understand kind of questions that all of us have when we are kids, and we continue to run for the quest in looking for answers. Some of the questions could be like, what is the world made of? Where did we come from? When we look at the stars, then we wonder, is there another universe? And the question always is, in doing research, in doing these kind of studies in science, the question is, what is an impact that we can do to mankind? And you will certainly know, and you believe certainly, that whatever we work in science and pure blue sky kind of research always has an impact on society. And once we have impact on society, the impact is taken immediately over by the country. And those countries really progress where the science, research and development is taken extremely seriously. And you all know examples like the United Kingdom, Germany, United States, and so on. So basically, I work at CERN, like was mentioned. It is the Center for European Center for Nuclear Research. Initially, it was called Nuclear Research, but now it's called High Energy Physics or Particle Physics. And that's where the word particle comes in. And it is completely curiosity-driven blue sky research. What is the meaning of blue sky research? It means that we do not have an immediate return of investment, so to speak, as we have in the industry, where you have a certain plan, you invest your money, and you know that after 2 years, I will be able to sell my product and get some money back. Here we are looking at curiosity-driven blue sky research, again in search of answers to many questions. And of course, in doing that, we intend to have an impact to mankind. The pictures you see here are several of the Nobel Prize winners at CERN in my field, and I was very fortunate to work with one of them. His name is George Sharpa. He is number 4 here in the list, and he worked on instrumentation. And of course, the inspiration comes from your mentors, your colleagues, and he has been also one of my inspirations in my career. So, well, of course, we are all standing on the shoulders of giants. The knowledge progresses as we go along, and it is built upon what has been built up in the past. We all know and have studied about Isaac Newton, who in 1697 gave us the famous apple from the tree illusion, and also how he derived gravity and how he formulated the laws of motion, which are followed by every single planet, every single galaxy, every single universe out there. And we have our life on Earth because of gravity. The Earth is round because of gravity. The moon is there because of gravity. The sun is there because of gravity. And of course, we know about galaxies far away, and we can infer about other galaxies only because we understand the laws of motion and how they impact the movement of the stars and so on. And of course, you have also heard about gravitational waves. Recently, it was a lot in the news as well. In 2015, they were discovered. We also have an experiment called LIGO India. But where is the particle here? You may have heard about the graviton. Just like there is a photon that gives us light, there is a graviton, which we still have to observe, which gives us gravity. And how do we know that? We know that if I am sitting in this room and if I seal it very, very carefully, if I convert this into a vacuum chamber, I will still be sitting. I will not be flying up, right? So there is something that is pulling me down. So gravity is still there. Hence, the field of gravity, the field that is pulling me to the earth, is still existing. We learnt Maxwell's equations. And of course, we were very confused when we learnt it, right? At least I was when I was first introduced to Maxwell's equations, which demonstrated the electromagnetic nature of light. This was in the 1815 by Clerk Maxwell, and they were elaborated further by William Hertz and, of course, Michael Faraday and so on. So the main point here is that we combined whatever information came year by year, century by century, and then the understanding of the forces around us and what pervades everything around us started improving. The laws of electricity and magnetism were finalized, and they were generalized and unified so that we could have four fundamental Maxwell's equations, right? You must have studied them at school or college. Now, we cannot speak about giants when we do not speak about Einstein, right? And you know how you all have studied about relativity at some stage, and it is not just some abstract theory. You all know that our global navigation system, the GPS positioning system, for that to working correctly, we have to have the correction that is given by special relativity, because of the way the calculation of distance is based on the time between signals received from various satellites, right? So we have studied relativity at some point, and the example, the impact on mankind comes much later. So blue sky research is very, very important. And of course, we continue these studies just because we know that eventually there will be a lot of impact of whatever we study in an open way in the field of particle physics or in the field of high energy physics. We have no idea where the impact will go. For example, financial and risk analysis at the New York Stock Exchange uses the algorithms that are based on quantum mechanics, that are based on artificial intelligence, and that are based also on the neural networks that have been created at CERN for the experiment for looking at the data. And if you go backwards, if you remember that Einstein had also got the Nobel Prize for Brownian motion, and that kind of motion is actually a seminal towards having these kind of understandings of randomness in nature. And that's the randomness that the financial and risk capitalists have exploited. Now we come to our own Satyendranath Bose and Einstein, who, together with all the knowledge that had come up to the point where we were around 1924-25, they combined quantum mechanics and they posited that there are particles that are fermions and there are particles that are bosons. It is a bit confusing, I agree, because when I study and I calculate, I'm able to do that. And I'm able to say that, spin half particles are fermions and spin one particles are bosons. But what exactly does it mean? To my understanding, imagine that you have a local train here. You see in the center, there is a local train in Bombay, in Mumbai. And here it is completely full of people, right? Usually this is the situation, isn't it? And then I want to put one more person on the train. It is impossible. It is impossible because each of these people are unique, and there is no more space, and they occupy a unique position or unique volume in the space that is offered by the train. But imagine that I have ghosts, booth. They can enter everywhere, correct? So you can put more and more and more, as many as you want. You can put more ghosts inside this train, but you cannot put any more humans. So the fermions, they are the fundamental particles that have, of course, certain quantum numbers, and they are described very, very carefully by quantum mechanics, but they can occupy only one space. While the bosons, they are the ghosts, like the photon, or like the gluons, like the Higgs boson that was already mentioned, like the graviton. Those are the ghosts that are everywhere. And we need to understand how they interact with the rest of the particles. So that's the kind of thing that we need to understand. And once that is understood, the fermions actually tell us how the universe is made. And the universe is made by the atoms, molecules, elements, all that you know already from the periodic table. And essentially, we can have a good description of the universe. Talking of the bosons now, how do these bosons that we study, if they are such tiny, tiny, tiny particles, how do they make any impact on mankind? Now we know that, like the ghosts, we can add photons together, right? And we can make lasers. We can do many things. We can have a remote in our hand and change the channel on the television. So these are extremely useful concepts, but it takes a very long time to come into society. So just to say that it is a great adventure to learn about particles, and from these particles, just you can take a look at my table here, the kind of impact that has happened because of particle physics to mankind. And we will speak about this in a little more detail later. But you all know about X-rays, about PET scanners, MRI scanners, therapies, and of course lasers I already mentioned, and gene therapy because of the DNA structure. So I hope I have convinced you that particle physics is very important. Quantum mechanics is very important as well. And Maxwell's equations are also very important. Now let's look at this picture, beautiful picture over here on my left, which I hope you're seeing it also. This is an orange and yellow picture on the left, which is an electron microscope picture of the COVID-19 virus. So why do I bring it here? I bring it because if we were looking at a microscope, just a light microscope, means we use photons for diffraction, and then the resolution that you get in your optical microscope cannot be better than 200 nanometers, right? Simply because these light microscopes are limited by diffraction. On the other hand, if there is a scanning electron microscope, right, and under the scanning electron microscope, we can achieve better than 50 picometer resolution. And that will give us the structure of things like the coronavirus, isn't it? And the protein structure that was mapped using the electron microscope opens the door to the first vaccine for the coronavirus. Because unless you understand it, how will you be able to treat it? So particle physics, on the one hand, has contributed to tools that mankind uses first to understand about matter, and then how to use those tools for benefit of mankind. Now in this picture, I think it is fairly obvious. We know about the macroscopic and the microscopic world. And when we speak about particle physics, it's somewhat starting at the level of the atom. The level of the atom we are all very familiar with. There's the nucleus, the electrons, and of course, the electrons are fundamental. There can be different kinds of leptons, and electron is one of the leptons, while the nucleus is mmade up of neutron and proton by themselves. And these protons and neutrons are made up of even finer particles that are called quarks. And we will look at them in a moment. How did we know this, by the way? So let's see, how do? We start to smash things together. I'm sure all of us have played at some level Lego, the younger generation particularly. In our generation, there was no Lego to play, We made boxes and tapas. But all right, let's imagine that we have two helicopters made out of Lego. And if we want to just smash them together, what happens? Let's see. So so you see, we smashed them, but they were not the fundamental particles. They were groups of particles. And again, there were very long studies that have been done studying the cosmic rays using balloon experiments, exposing photographic plates in the atmosphere, and so on. That has told us what are our elementary particles. Using the study of cosmic rays, you see, these are cosmic rays, and we are showering with the cosmic rays. Neutrinos go through our body, trillions of them, and we don't even notice them. So all those studies have been done using cosmic rays and also accelerators. We'll come to the accelerators. But just to point out that when the collision energy is higher, you get into the smaller and the smallest of constituents. So we understood how can we build our atoms. In this particular example, you see, there are quarks like up and down quark, 2 of the 6 existing quarks, by the way. So these 2 quarks together, along with an electron, make up the helium atom. Shall we make it? Let's try. So this is the nucleus, because you have now the protons and the neutrons inside the nucleus, and I have 2 electrons. And with these 2 electrons going around the nucleus, we build our helium atoms. So if we know how to build helium atoms, we can build the whole periodic table, we can build all the elements, and now we have understood how the universe works, essentially. So particles really explain to us how the whole universe works and what is the recipe, so to speak, of making atoms, molecules, and the world around us. But in studying those things, we have a lot of impact that has come into the society. And I will not go into any detail over here that goes from civilization to engineering, to travel, to food, to exploration of space, and so on. So in addition to the particles, there are 4 fundamental forces. And these forces are electromagnetism. Now you know that, of course. That's how the atoms come together, because of the nucleus and the electron, and they are held in the orbit because of the electromagnetic force. The strong nuclear force, it holds the nuclei together, because even though the protons are positively charged, they don't repel each other. They are bound with the nuclear force. The weak nuclear force gives us radioactivity. It's a very weak force, and that is manifest in the center of the sun. And that's how the sun keeps shining and gives us light, gives us warmth, and we are able to have life on the planet. And of course, gravity, it holds all the planets and all the stars together. So indeed, the picture looks very nice and very complete, because we know how to make the universe, we know how to make the solar system, we know how to make day and night, and we know how to have life on Earth. However, it's not so simple. And of course, there are many questions that still remain. So we are on this page on the right-hand side, like this man who is thinking. He is thinking, how did we get here, right? Just like many of us think all the time. So we know about states of matter, like gas or liquid or solid. But are there other states of matter? We do have some ideas about plasmas. But then are there still other states of matter? And that is what we are trying to study at CERN. And not only at CERN, but in the rest of the world, we have collaborations where we try to understand what happened exactly at the time of the Big Bang. So at the time of the Big Bang, immediately after, 10 to the minus 43 seconds after, you see that there is a soup over here. At home, sometimes we have soup, right? And we do not know what are the ingredients. And we try to understand what exactly is in there. Are there carrots, or are there potatoes, or are there tomato, or peas, or whatever? We have to find out. Similarly, this period of the evolution of the universe just after the Big Bang is what we are interested in, and we try to understand. We want to recreate with our collisions. Remember the helicopters? We want to recreate this period. How do we get so much energy that we are able to recreate that plasma that existed after the Big Bang, before the elements were created? 3 minutes. In 3 minutes after the Big Bang, elements started being created. So what was happening before? There was something called the cosmic soup, which is over here, where we have no idea what's happening. There are some particles there going around, but those particles do not exist anymore. Just like the dinosaurs don't exist anymore, but we know that they are there. They were there because we found the signatures and we found the fossils, correct? So similarly, there are particles here, and we know many, many particles that were there because we find them in the cosmic ray interactions, right? So we have deciphered what was there in the time over here, but we do not know how. There are still many questions. Similarly, in the period 10 to the minus 10 seconds to 10 to the minus 5 seconds, something like few microseconds, what was going on over there? That is a quark gluon plasma. And also experiments at CERN are looking at these particles and trying to understand how this behaves. This state of matter, how does it behave before it actually moved into making the quarks, which eventually made the atoms and the molecules, which then made the elements, and then of course the whole universe came about 15,000 million years ago, 15 billion years ago. So open questions are, of course, that physicists found more than 200 type of particles, okay? Of course, they are not all stable. The only stable particles we know are the matter of which we are made of, or the world around us is made of. But then even in those particles, we do not understand why the proton has a certain mass, which is so much higher as compared to the electron. And how at all did it acquire this mass when it was in the soup, right? So that's one of the very big questions. Another question is that when we put together all the information we gather from cosmology, from astronomy, from physics and astrophysics, we find that there should be something more out there. Just like if there were a magnet under the table and there was some cutlery on the table, it would start moving and you would say, I know there is a magnet under the table. Similarly, galaxies are moving, and from the movement of galaxies, we are able to find out that there should be at least 95%, which what we are not able to see. So imagine we are only able to observe 5% of up to today, 15 billion years ago, we are able to observe only 5%. Where is the rest? We call it dark matter and dark energy. We have no idea what it is. We still need to find out, and we still need to study. And if we find candidates of dark matter at CERN, this would be fantastic. It would be like a new door opening into a new world of trying to understand how this whole thing came around. In addition, there is a question that comes to everyone's mind: why at all are we here, right? Usually matter, whenever it's created, there should be an equal and opposite amount of antimatter created in the same time. Conservation laws, simple, isn't it? So if there is equal matter and antimatter, it should have annihilated, and we should not have been there. But we are here, and that means that there is a certain difference or a certain asymmetry between matter and antimatter. And what exactly is this asymmetry we are trying to study? And of course, as I mentioned already, we are trying to understand the primordial plasma, as I showed you before. So yes, using all these kind of questions, curiosity-driven research at the Large Hadron Collider, where we collide our helicopters, so to speak, is what we do at CERN, and we are trying to investigate further this Big Bang theory and the understanding of particles and the structure of matter, right? So we mentioned about the quarks already. We mentioned about the leptons, of which electron is one of the particles that makes us up. We are full of electrons, we are full of quarks, because we are made out of protons and neutrons, right? Now, of those, there are fermions, remember? And the bosons. The bosons are actually the particles that are the force particles, essentially. And because of them, the force can exist. The electromagnetic force can exist because of the photon. The weak nuclear force can exist only because of the W and the Z bosons. Similarly, the strong force can exist only because of the gluons. But how did mass come about? Remember? And for that, way back in 1964, Peter Higgs wrote this equation, which you see on the left over here, explaining how using another boson here, he didn't call it the Higgs boson, we call it the Higgs boson, we could ascribe mass to particles, right? So that would be called, in 1964 he postulated it, and then it would be called the Higgs boson. So he was not alone, there was a team again, and this team was postulating the presence of a Higgs boson with a Higgs field, and how much a particle interacts with the field will be the factor that depends on how much mass it will get, right? So now, if this field is invisible, how can we prove that it exists, right? How could we prove that electromagnetism existed? So similarly, we went back to making our experiment. In this experiment now, let's increase the energy, okay? If we increase the energy, then you have to be reminded of the formula by our Einstein. He said E is equal to mc squared. So if we put a lot of energy in our collision, so to speak, we should get this energy converted into mass using the Einstein's formula, right? And then we can have photographs being taken all around this collision point, so that we can equate our equation. We know the energy that we put in, and then we measure the masses of all particles that are coming out, and we will be able to say, yay, we have measured all the... what happened? There was a collision, but something very special happened. We didn't expect this, were we? We didn't expect. We were expecting the smallest constituents, but that didn't happen. Something else happened. So it means that from the energy, we were able to create those particles that existed at the time of the Big Bang, and they are not there anymore. So how do we do it? We have now understood how to create particles from energy, and we are going to make an accelerator. And this accelerator will accelerate the protons in such a way that there is so much of energy that we can give to these protons by using very specialized magnets, that when they collide, when these protons collide, they will have temperatures over 1 billion times inside the center of the sun. So they will be able to produce the particles that may have existed at the beginning of the universe. So just like we produced some dinosaur particles, so to speak, we might be able to have some unexpected particles also. Dinosaurs we know existed, but these funny things, we have no idea whether they existed or not. So this is a fantastic experiment, isn't it? And we will be able to look at the highly expected particles, like the cats and the dogs and the rabbit particles. But then there will be these unexpected particles as well. That's what's the fun part, which means looking for dark matter, looking for new theories like the supersymmetry and so on, right? So this Higgs boson is very, very heavy. It was predicted by the theories to be very, very heavy. It's also very rare. It's as if to find one grain of gold in all the rice that is eaten by all of India. It's that kind of rare, right? And of course, it doesn't stay there to say, hey, I'm here, can you detect me? No, it immediately decays into lighter particles. So we need to have a very specialized experiment, and that was done at CERN. And despite all these difficulties, we found it. And how can that be done? We have to have the accelerators to produce those particles clearly. We need to have detectors which act like cameras to take pictures which come out from these collisions. We need a fantastic computing infrastructure, software and smartwares to collect, to store and analyze all the data that is coming out from the detectors. And of course, this is not possible without a fantastic collaborative effort where at this present moment of time, we have more than 5,500 physicists on one experiment. And there are two experiments. So this is where I am right now. If you will look very carefully, I'm sitting right here. But okay, I'm joking. I am here on the picture, but and my home is right here. This is the airport of Geneva. And what you see is a schematic circumference of 27 kilometers. That is our accelerator. It is 100 meters underground, because obviously there is no point to make it on the surface and take space. So it's put underground. And what you see circulating, blue and red, are representatives of the proton bunches in two different directions. And when they collide, that's where we have our experiments. If you look carefully, there is a dotted line here. So on the right-hand side, you see Switzerland, and on the left-hand side, you see France. All right. And am I right? Maybe not. Maybe it's just the other way around, because Geneva is in Switzerland. So left-hand side is Switzerland, right-hand side is France. And these particles are going around without any passport or visas, but they go and they give us a lot of information about physics, particle physics, and that's where these experiments are then located. That's a picture of the inside of the accelerator. Here are two beam pipes where the bunches are running, whizzing around. And of course, this happens it's making all sorts of world records, of course, because this happens 11,000 times in 1 second, 27 kilometers. You can make a calculation that the velocity or the energy of these protons is 99.99999% that of speed of light, right? It is colder than empty space in the universe, simply because we need to operate superconducting magnets to be able to have the vacuums that we need. Otherwise, this won't work. And of course, the current that we need to kick the proton bunches is of the order of 20 kiloamps. Imagine at home when we are cooking, you know, that draws how much? It draws 4 to 5 amperes. So yes, it's an extraordinary machine. I will let you read about it later in detail. I just want to focus on the point that there are 4 experiments. Underground, you see that there are these the infrastructure of the accelerator, and on the surface are the 4 experiments. Atlas, LHCb, and CMS is hiding somewhere. It's here, CMS and Alice. And of course, all this is underground. These are the pictures of the experiments. If you look very carefully, you will see a very tiny girl over here. I don't know if you can see her, but she is about 4 millimeters in this space. Oh, there are a couple of people here as well. So just to say that if you think about this as a big ship, 6-storied big ship, that's the size of the experiment. CMS is my experiment where I work, and this is more compact. Nevertheless, the weight is more than 14,000 tons. And the overall diameter is 15 meters, and overall length actually is much more than this, what is written here, because we have kept on adding more and more. But it looks like a cylindrical onion. Imagine a huge cylindrical onion with a magnet inside and with very sensitive detectors that are taking pictures of the collisions 40 million times a second. Why do we need to do that? Because we need to have a lot of data to be able to look and find the Higgs boson. If we do not have a lot of data, we won't be able to find it. So just some pictures of my experiment. That's where I work. That's has been my Karam Bhumi for last 20 years, in fact. You see how we lower from in the shaft from above these very big pieces, which are of the order of 2,000 tons, and specialized companies are needed. That's my favorite detector, the one that I have actually steered and installed recently. And you can see downstairs, working conditions are not the same as you work on the surface, but yes, it's been incredible, and you will be able to find this link very easily. Similarly, data challenge, I have mentioned to you that the data we collect today is of the order of 60, 70 petabytes per year. So we need to have a very smart way of how we share the data, how we compute, how we manage, and CERN only can provide 20% of the capacity that is needed. And CERN has, of course, invented the World Wide Web, which all of you know, I assume. It has also invented grid computing, which means that you are able to use all computers sitting over the planet for computational purposes. And this is for high energy physics, as you can see, also in collaboration with Imperial College London. And you can see how many jobs are running and so on. So this is a very big endeavor. And clearly, as you see, now we have the CPU scaling is coming to an end. We have now to move towards exabytes, and the GPU, we have to now go to GPU processors. We have amazing artificial neural networks that actually look for those collisions. And here you see a picture where perhaps a Higgs was formed, and you calculate all the energies and you record all the pictures that you've been taken, but you use very fancy algorithms which employ machine learning. So some pictures. Now this may look very, very technical to you, but it is very special. Because when you look at a little blip over here in Atlas, and the same blip over here at the same energy in CMS, you know that something special is happening. And this happened in summer 2012, when, after collecting a lot of data, the Higgs was actually discovered in both experiments. Of course, if you find it in one experiment, nature doesn't differentiate between the two experiments. You must find it also in the other. And this was incredible. And this was an announcement that was made in a seminar at CERN. And I found a place outside the door, because even though I went at 5 o'clock in the morning, it was already full. So you can imagine a big moment for the particle physicists. There was a conference going on in Australia, and this conference was live done for the people in Australia. And of course, in India also, there are a lot of people who have been working on this in many different institutions, and they have also contributed to this big discovery. So yes, the Nobel Prize of 2013 was given to Professor Peter Higgs, as you know, and Professor Francois Engler as well. This is a seminar that was done at CERN by the then Director General, Professor Rolf Hoyer, and we are all celebrating here in this big, and you see the Higgs is really there and happening. And eventually, of course, the Nobel Prize was given to Peter Higgs and Francois Engler for the theoretical discovery of a mechanism, right? But it was recently confirmed through the discovery of the particle by the Atlas and CMS experiments at the CERN's Large Hadron Collider. So this is very important. Instrumentation, engineering, all these things are extremely important, to go along with the theories that are being predicted by the theory people, right? For the future, we have to study the Higgs. We have to look at and examine. It's like a newborn baby. So now we need to find out what are the other things that it can tell us, and the other theories that I already mentioned to you about supersymmetry and about dark matter, right? So yes, now we just speak a little bit about innovation. I think I have tried to tell you about our tools. The tools are the accelerating particle beams, the detectors that take pictures of the collisions, and of course, the computing grid, and of course, all the software tools that have been coming out from these experiments. So let me give you a few examples of medical applications where we combine physics, particle physics. You know, we talk of antimatter and we use antimatter in medicine to look at tumors and to have the PET scanners which are based on antimatter. So these are real things. We are not just talking about some fancy theories. So accelerating beams, if you target these accelerating beams into a tumor, you know, you can target just the tumor, not the healthy tissue. And radiation therapy damages the healthy tissues. So this is a very big improvement, and this is happening right now in Europe and in United States and in Japan and so on, where more than half of the accelerators worldwide are being used for hadron therapy. Hadron is a generic name, as I mentioned. Similarly, just like we take pictures of collisions, similarly, if we inject some radiation loaded medicine in the body, we can be taking pictures of the photons that are released from the body by using this PET scanner, and we can look for brain metabolism in situ, for example, for Alzheimer's disease research and so on. Here is an example where, if you look carefully, you will see the logo of CERN over here. And this is the measurement of radiation of astronauts and cosmonauts who go up in space, simply because there is more radiation and they need to uh, control how much exposure they have. Now, this is just part of a silicon pixel detector inside the heart of our cylindrical onion experiment, CMS. And in CMS, it has played the role of the Higgs discovery, as you see over here. This is just the laboratory where it was built. And if we use the same detector to make beautiful images, you can see the contrast that it can offer by using our pixel detector with fancy chips, of course, with fancy electronics. One of these is called the Medipix. So just examples of how this information can really be very useful. You can imagine the contrast it can provide, the algorithms that can be used to pinpoint the difficulties in tissues. This is just a rodent, but this can of course be translated to a human being. Now you see this picture. It's a fantastic picture which gives you a 3D picture, 3D scan of a person, where of the wrist of a person, and this has been of value equal to the Higgs announcement in terms of a return on investment eventually, isn't it? So yes, let's take a look at the ankle from a doctor's point of view. He wants to see exactly where the bone is or where it has been damaged. These are the new techniques which will be used in the future, and these trials have already begun. Those rates I have already mentioned. So the World Wide Web, I think I will not skip this, because the World Wide Web was a 23-year-old student, just like one of you, who was at CERN. He was working, and one day he went to his boss and he said, look, I think I know how to make an algorithm which can, a protocol called the HTTP, which can help two computers to talk to each other. And the boss said, vague but exciting, let's go for it. And you see today, if you go to this site, I think all of you are also scanning the web every day, but the impact of the study of the coronavirus worldwide, the data, the variety, the sorting, the medical management, policy making, strategy making for governments is controlled now by the World Wide Web. And not to speak about the economy of trillions of dollars that actually has been the impact. Speaking about other things like bioinformatics, I will not go into detail for lack of time, but you can imagine that if you want to find a drug, and for that you need to do a lot of simulations, how will you do that? You will use grid computing, malaria drug research, and so on. All those are taking now they are exploiting grid computing in order to be able to get some sort of results of the simulations from all the data that they have. Weather forecasting, particularly important for India, as you know, because of the cyclones and the floods and other kind of damages that happen to human life and economy. And of course, in education and training as well, this is very important. Today, no student can say that I do not have access to knowledge or access to tools of knowledge. Today, you just go to the web and you type, can you explain to me the Legendre equation? And there you go, you have it, right? So yes, I think there are many, many examples which I could give you, but I invite you to take a look and go on Google and take a look on all what we do at CERN in many, many different areas. These are space experiments. And of course, we have visits from important people coming here. Here is just an example of a young lady who has not even finished her studies. This is 16th June 2020. She came to CERN for a small period, and then she understood that she could do some data crunching and use that temperature mapping of every person just by using a telephone, by an app. And this app is now available, and this app is making her money also and making her a millionaire. So you can Google this up as well and see how basic scientific research can result in very big impacts. And of course, in our own country, we have a lot of work going on. There is a lot of enthusiasm in trying to understand the way to deal with the pandemic. One problem I want to state is about the fact that in India, we have only 40,000 ventilators. 1.3 billion population, 40,000 ventilators. In the United States, there are 250,000 ventilators for a population of 250 million. So if I'm correct, or maybe 270, I don't remember the number. So the point to make is that it's not the question, no, in normal conditions, I think we would manage. But in pandemic conditions, India absolutely needs something like this, something like a ventilator that can really help the masses as such, so to speak. So yes, there is so much of room where people would like to have homemade ventilators. And at CERN, we have invented something called the high energy ventilator. Simply because we have the competence, we have literally the world competence on making gas systems, very, very complex and sophisticated pneumatics, very complicated engineering and so on. But this is not a very high-end ventilator that has been proposed. It's a simple ventilator. It's called high energy simply because it's coming from high energy physics, but then it is developed in full consultation with clinical and medical field professionals. And this design is ready to go because we are just at the point of testing it out in the hospitals. So if anybody has an idea to set up a company and go for it, this is the moment. All right, so yes, collaboration is very important as well. I want to come to that aspect now. So how were we able to do what we have done? I am using the word we simply because even we does not justify the fact that I personally, I'm getting more credit than I should, because it's not me, it's all these people who work together. It's the people who thought about the LHC, the machine. It's the people who thought about the CMS experiment, who thought about the magnet, who thought about, every single detail of this experiment. And of course, all the teachers, the colleagues, the students who do all the analysis. So collaboration is extremely important. And that is something which in India we have to learn a little more, since we have the opportunity. We have many projects going on in India, in not only in particle physics, but in mega science. There are many, many other projects. So we need to get together a little more and maybe grab the opportunities to learn how we will be able to work in a collaborative mode, just like that the fact that we were able to discover the Higgs boson starting in 1964 up to today. So there is a strategy that is put in place, and that strategy actually works. So we need to understand what are the good things about it and how we will be able to bring those practices into everyday work that we do. This is just a flash. It is a fresh off the press from yesterday, because yesterday the strategy was announced for the next future collider. And this is the Future Circular Collider. It's 100 kilometers circumference. It's going to be built and be ready in the 40s, in the 2040s. So the younger kids among you are the ones who want to learn about what's going on and how you can engage. So yes, as I already mentioned, we need to partner and build from mega science blue sky research. CERN is one experiment, but there are all these that I have listed over here, and we have a lot of Indian participation, lot of possibilities to go in India to the universities where you can, and the institutions where you can have opportunities to work on these things. From there you begin and then you move further. So we look at the science, the technology, the industry, the engineering, and of course the education aspects of all these. So yes, I would like to encourage you to take part, to learn, to engage, and eventually I hope that you lead these big endeavors that are going on. And it's not difficult, it just appears difficult, just like it appears difficult to everybody, whoever has been working. So yes, I would like to encourage the young people because they are key for tomorrow, and they are the key who will actually unlock the mysteries of the universe, right? That's about me, just a flash. I come from Jhansi. You may have heard about Jhansi. It is in Uttar Pradesh. That's my school over here. And that's me in my school. That's me in my university, and so on. And that's me at CERN. That's the first time I came to CERN. And then I have been working here in many different capacities, but mainly, like was mentioned, mainly in R&D, where I have been working a lot on micropattern detectors and eventually building large systems over here. Here you see me in the control room. Here you see us with many guests and so on. So there are a lot of opportunities which are over there. And I want to also share that if I can do it, anybody can do it, because the journey has been pretty difficult. No one to guide us, no one to guide me particularly, because it was completely uncharted territory. But today the tools are there, information is there, the World Wide Web is there, and particle physics is a field which is very unique. You start from a little idea and you end up, you have no idea where this idea will take you, and you can become a leader in the field of your choice if you have a career not only in particle physics, in any of the mega science blue sky research projects. Particle physics is just close to me simply because I'm working there. I will be biased, right? But nevertheless, the quest will continue and I have miles to go. So thank you very much for your attention, and I hope that there will be some questions. Thank you.
Ma'am, it was an amazing lecture. You have to see the chats and comments that it is received in YouTube. It was there so many appreciations. They are seeing you for the first time, and they are having few queries also. So I have taken some queries and I have listed in the chat box. So first of all, one question is, why antimatter disappeared after Big Bang?
Yes. So antimatter, I think, behaves differently than matter. So for every 10,000 particles of antimatter, 10,001 particles of matter were created. So of course you will read more about it and more, let's say, in detail by the experts. But it is just to say that antimatter is a bit different than matter. All right. So we have been creating antimatter at CERN in one of the experiments, and we created routinely in many other experiments. But one particular experiment is focused on the study of antimatter. How does it behave under gravity? How do you confine it? Can you make antimatter molecules, for example? And actually anti-hydrogen was made. So please Google up about it and you will get more information.
Okay. The question, what is CMS and how it works?
Sorry, I missed the beginning.
What is CMS and how it works?
CMS is one experiment. CMS is one experiment. It's a very big experiment. It is, as I was explaining earlier, it is like a cylindrical onion. So think about the fact that the accelerator is working and there are collisions happening 40 million times a second, and we want to take pictures of those collisions, correct? Now, if we want to take pictures of the collisions, we need sensitive detectors around the collision point, isn't it? We need to take where every radiation that is coming out from these collisions can be recorded. And the time stamp is also there, correct? So you need not only to take pictures like you take from the mobile camera, right? You take maybe 3 pictures per second. We need detectors that can take pictures 40 million times a second. So those detectors are there. We have made those detectors, and we are able then to look at the data that is coming out by the use of very, very advanced firmware firmware that we use on FPGAs. You look up a little more on the electronic side of it, which only spit out part of the data that is useful for us, and then we analyze it. I showed you some pictures of the analysis. Yeah.
Yeah.
Okay.
So, ma'am, from SAR itself, economically to have a particle asset to hospital for medical application.
Okay, sir. Thank you for the question. So the situation is as follows: that an accelerator is indeed a very expensive instrument, correct? So how do we manage this? What has happened in Europe, I can tell you, that the technology was available for health treatments and also for studies, for R&D studies, medical studies, um, animal studies also. So
Yes.
those accelerators were created in different places in Europe. Some companies like Siemens is a company, correct? And then there's another company called IBA in Belgium. They picked the technology and they created a product. Like we are in the
Yeah.
situation now for the ventilators, they picked up at that point the product and they created a black box kind of an accelerator, which if I am a hospital, I can buy, correct? And I can install it in my hospital and I can charge very big money for the cancer patients. In India, there is one machine which is in Apollo Chennai, and
Okay.
this machine has a very high cost, first of all, and the treatment of the cancer is also very high cost. So anything between 20 lakhs and 50 lakhs, depending on the tumor, obviously, right?
Okay.
So the masses cannot afford it. So one common goal could be that, we all come together, whoever would like to join hands, and we contribute towards building such a machine in the country, and that would be a fantastic goal to aim for. It will be expensive, but once you have made one, after all, we are launching satellites, isn't it?
Yes.
We
Yes.
didn't know how to do it before. Now we know how to do it. So
Yes.
at some point, we have to get started.
Okay. So another question is, diamond and graphite are made up of carbon, where diamond is the hardest and the crystal, another one is crystal. What is the theory behind it?
Arey Baba, this you have to look yourself. This is a very simple question. A cool 8th grade question. Go back to school, please. Sorry.
Okay. So another one is, what kind of research about neutrinos is going on in LHC?
Okay, so neutrinos is very interesting, as you know, and neutrinos are the least understood particles because we cannot see them, isn't it? We cannot see them. We can only find one in a billion events. So there is a lot of work going on. There is a lot of studies going on also for making new experiments with neutrinos, and one is called the Dune experiment, and that experiment is going to be in United States, because and we are participating, which means that at CERN we are building part of the Dune experiment, which will go there. And in addition, India is also participating in that experiment. In India, we have our own INO. You may have heard about it, the India Neutrino Observatory, which also is looking at neutrinos. So overall, at CERN, the focus is more on the high intensity frontier, and in the United States, they are focused on the high energy frontier and the high intensity frontier. So in this way, neutrino physics is more in the United States, although here there is whatever complementarity can go on is going on.
So another question is, if Higgs field give masses of particle, so why the particle like gluon and proton are massless?
So they are the way they interact. See, suppose if we have a room where we are thousands and thousands of people together, let us assume. We have come to the museum, science museum, let's say, and we are full, completely full, chock-a-block. And then enters from one corner in one door, enters Shah Rukh Khan, for example.
Okay.
What will happen? The people closest to Shah Rukh Khan
Yes.
will go completely crazy, right? They will go and say, "Can I have an autograph? Can I take a picture? Can I take a selfie?" Correct? But the guy who is on the other side of the hall will not be able to interact as much as the person right in front.
Yes. Yes.
So depending on the mechanism of how much the particle interacts with the Higgs field is the mass that is given, right? It is just an analogy, please.
Okay.
Okay, there is one question, Kishan.
Yes, sir. Yes, sir. You can go ahead.
One question from Dr. Jagannath. He is there with us online in the webinar. He is asking, how do we increase or meet the number of ventilators required for us, and what are the ways? This is related to COVID.
Yes. So for the ventilators, I can already tell you that if any one of you is interested to build the high energy ventilator, I can facilitate that very easily. And if you will not tell anybody, there will be no price. Okay, it will be. So you have to contact me, and you have to really be serious about it, because you know that, like you, I also I have a real job to do, and this is all my fun things that I do. But if you would like, please get in touch. Okay.
Okay. Okay.
Okay, thank
But
you.
don't tell anyone.
How will you manage the massive temperature produced due to the collision?
In the
How do you
particle
manage
accelerator. Okay.
Yes,
Massive
because that is the reason why we use superconducting magnets, and these superconducting magnets are cooled to 1.9 degree Kelvin, and there is a lot of helium that we use for these for cooling the magnets, and heat sinks are there all over, of course.
Okay.
Yeah, I mean, there are details which we can go through, but maybe there's not so much here. Yeah.
Okay. And the last two questions, ma'am. One is many people are from India, especially from India. They may ask this question: why Zen research Nataraja statue? Can you please?
Yeah, of course, you know. तो हर प्रोटॉन जो है अपने ब्रह्मांड में, हर प्रोटॉन जो है वो कहाँ से आता है? कोई ना कोई तो नृत्य हो रहा है, ठीक है ना? तो वो जो नृत्य है, प्रोटॉन उसी की अभिव्यक्ति है, isn't it? तो अपने हर भारतीय के लिए तो यही कहना सही रहेगा कि वो एक कॉस्मिक एनर्जी की अभिव्यक्ति है, और हमारे CERN में वो इसलिए है क्योंकि वो डिपार्टमेंट ऑफ एटॉमिक एनर्जी से एक भेंट में दिया गया था CERN को, एज एन अप्रिसिएशन ऑफ ऑल द कोलैबोरेशन दैट वी हैव विद CERN.
Okay. And another last question, ma'am, what is the procedure for internships and other opportunities for Indian students?
जी, तो एसोसिएट मेंबरशिप तो हो गई है ना इंडिया की फ्रॉम 2017. So now you just go to the web and you type career CERN. The first link you will get is how do I apply to CERN.
Okay. So because many of the students are also asking that they want to work in Zen, so it might be very useful.
Absolutely, and I will be more than delighted if there are applications from India, and because I know that how good our students are, and they can only give us a very good name for the country also when they come here and they participate. So yes, I will encourage everybody to look there. Go to it's called careers.cern as far as I remember. Careers.cern, careers.cern, I think. Let's see. I think, I mean, students are smarter than me, I'm pretty sure.
Yeah, they can search, yeah.
They will find no issue.
Yeah.
But I wanted to just add one question related to that only. Whether only the candidates who have research experience in the field of physics, they get the opportunity to work there, or other field of science also, whether they can come and work there.
Sir, it is, as I was explaining, that there is a big, huge possibility of engineering, of project management, of material science, and so on. So it's all right. I mean, you let me see here, for example.
Even biological science also they can come, isn't it?
So biological sciences is not so much, I would say.
Not so. Okay.
Yeah, but if you go, you can see here. Can you see my screen because I'm sharing?
Yes, ma'am. Yes, ma'am. It is visible.
So
Yeah.
you can see here, if I go to opportunities for students, you have a lot of stuff here. If you go for professionals, you have a lot of stuff here as well. So you see staff association, scientific association,
Yes.
fellowship
Yes.
program,
That's true.
technicians. I would really appreciate if young students want to come here and spend a couple of years only for learning all the technicalities. This would be fantastic.
Sure, ma'am. After this, you can expect more number of Indian students because
Yeah.
near about 1,000
Yeah.
people are watching from in the live. So you can expect more students from
I am
India.
always, I'm saying that for last 20 years. So I can see that the graph is going up. So I'm very happy
Yes,
to say that
yes,
I'm
ma'am.
very happy
That
to
is a great thing.
contribute a little bit to that. Yeah.
Yes, ma'am. That is a great thing. I think for women, like girls, education also, those who want to come into the STEM field, so you will be a motivator for them. So while watching that, many students will get motivated and they will also try to do their best in this career.
Good. I'm happy. Although I mean I still have miles to go and I have to still keep learning a lot. And
Yes,
whatever little I have learned, I want to share with everyone and also show, because many people don't even know about it.
yes,
So this is important. The outreach and education is very important, and I think that we have the science museum also engaged. That is
yes,
fantastic. So they
yes,
can disseminate more information.
yes.
Yeah.
Sure. Thank you. I request
to our most valued guest of today's webinar. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Francis Xavier Engineering College and the entire fraternity of the institution, first of all, I extend my most sincere thanks to the Almighty God for making today's event a grand success. I take this opportunity to express my sincere thanks to our today's speaker, Dr. Archana Sharma, Principal Scientist, CERN, Switzerland, who spared time from her busiest schedule to grace the occasion. Today, we had an opportunity to hear your wonderful thoughts and your experience. Thank you very much, ma'am. Next, I would like to record my sincere thanks to our beloved General Manager Development, Dr. Jayakumar, our Principal, Dr. Velmurugan, our Head of the Department, Dr. Geopatrick Nanraj, and also my sincere thanks to my colleague, Mr. Robinson Jaising, Mr. Punma, and Ms. Aishwarya Dara for making this technical webinar a grand success. I express my deep gratitude to our pillars of the department, Dr. Nidhi Manikam, Dr. Zinatul Farida Abdul Ghani, Dr. Samuel Hanson for their wonderful support for the successful completion of this webinar. Thank you very much. I also extend my sincere thanks to all my dear colleagues for their enormous cooperation and support. I would also like to thank my dear students Alban and Jason for their enormous technical support for make this webinar a boundless success. Last but not the least, my sincere gratitude goes to all the participants of today's webinar and also the subscribers from various institutions, universities, research scholars, industrialists from all over the world. Without you, this effort is not possible. Thanks for participating in this webinar. See you soon in the next webinar. Thank you very much for this wonderful opportunity. Stay home and stay safe. Thank you.